Picture dropping a 120-degree piece of glowing hot copper metal straight into a cup of cold 20-degree water. The immediate question in calorimetry is figuring out where this system settles. What is the precise final resting temperature of the copper and the water? Standard formulas often yield negative temperature values, creating algebraic traps that derail the final calculation. Methodically, there is a three-step method to solve this. By formatting the setup correctly, we ensure a balanced thermal equilibrium equation without the risk of any negative sign errors. This chart shows lists of specific heat capacities for common substances. Before we start calculating, we need two tools, a standard calculator and this reference table, specifically the columns that give us the exact C values for our copper and our water. Gathering this reference data up front and preparing for the sign error trap sets the foundation for solving these thermodynamic equations. Step 1 is mapping the directional flow of the heat energy. The foundational law of thermodynamics dictates that heat always transfers from the higher temperature object to the lower temperature object until thermal equilibrium is achieved. To prevent variable cross-contamination, we divide our workspace. We create a red column for the heat lost by warmer bodies on the left and a blue column for the heat gained by cooler bodies on the right. We place the hot copper, starting at 120 degrees, strictly on the left side under heat lost. We place the cold water, starting at 20 degrees, strictly on the right side under heat gained. By physically segregating the starting variables on the page, we eliminate the mismatched data entries that often disrupt calorimetry attempts. Step 2 requires selecting the appropriate thermodynamic formula based on the object's physical state. We have to differentiate between a phase change, like solid ice melting into liquid water, and a simple temperature change, where that water just gets hotter. This chart shows the heating curve of water, illustrating how its temperature reacts as heat is added over time across different states of matter. During the sloped segments, the temperature is actively changing. This means we apply the specific heat formula, mass times C times the change in temperature. But during the flat plateaus, the temperature holds steady as the substance undergoes an active phase change. Here we use the latent heat formula instead. Since our copper and water are only changing temperature, not state, we rely on the specific heat formula. This brings us to a crucial formatting rule. Standard physics conventions tell you to format the change in temperature as final minus initial. We bypass that entirely using the high-low rule. For the hot object losing heat, we write the temperature change specifically as its initial temperature minus its final temperature. For the cold object gaining heat, we write the change as its final temperature minus its initial temperature. Subtracting the lower number from the higher number on both sides ensures an absolute positive value, neutralizing the common risk of sign errors. Step 3 brings everything together by applying the principle of thermal equilibrium to calculate the final resting state. The balancing principle states that the total sum of heat lost by the warmer bodies must exactly equal the total sum of heat gained by the cooler bodies. We substitute our specific values, taking the mass and specific heat of the copper multiplied by 120 minus T final on the left, and setting it equal to the water variables multiplied by T final minus 20 on the right. Now we distribute the variables across the parentheses and combine our like terms to isolate T final on one side of the equal sign. Before calculating the final digit, we run a logic check. A correctly calculated final answer must land mathematically between the original hot and cold starting temperatures. Thermal equilibrium behaves as a predictable balancing point, governed by the conservation of energy. Solving our specific equation yields the exact final resting temperature for the copper and water mixture. This temperature falls logically between the original 20 and 120 degree boundaries. Because the total energy lost by the copper is exactly captured by the water, the result demonstrates that our high-low formatting accurately balanced the energy transfer. Map the flow, apply the high-low formatting to your temperature changes, and balance the equation. Test this method immediately by attempting exercise 11.3 from your syllabus. We can now predict the final equilibrium temperature, but we haven't yet discussed the speed at which the heat actually travels to get there. In our next tutorial, we cover heat conduction rates, examining how fast energy transfers through solid metals. Understanding this final balance of energy is the first step toward calculating how that energy moves through physical matter.